Now we are going to go component by component. The first one is the transformer model. So the transformer model, it exists many different models in EMT type tools. Like often it's compared to what type of study, according to the study you do, you will use a model or another. Here in EMTP we have three. We have what we can call the classic model, T-shape, where you have impedances on each side and an ideal unit in between. Then we have what's called a topological model, where the magnetic circuit of the core is built using electrical components. And so basically you have a duality between electrical and magnetic. This model is very nice because you can simulate a local saturation of each branch, so it's much more advanced, require more data, of course. This model almost requires no additional data compared to PSS type study, a little bit more, you will see. And we have the last one here, the high frequency model. The high frequency model, we will use it for lightning studies, for fast transients, and so on. How do you build this model? It's not so easy. You have the kind of chip model. It's using an arrangement of capacitances. You will put some capacitances in order to have like that some natural frequencies that kind of match the frequency measurements. Then you have what we call the frequency dependent network equivalent. In this case, you will enter many points in this impedance frequency curve, and it will automatically create a state space equation. I will come back to that. Okay, but most of the time for renewable energy studies, we are going to use the easy model. So that's the good news. So how does it work? It's a three non-ideal transformer unit representation. So inside this model, you have three non-ideal units, which are connected according to the connection type. Of course, it's delta Y, so you see how it is. Inside each unit, that's what you have. You have a impedance, RL impedance on the primary and secondary, and you have a magnetization branch here, okay, shunt. And of course, the ideal unit that transform voltage. That can also be a difference if you are used to work with some PSS tool. In PSS tool, you don't really have this these units, because those are based in per unit, basically. So this one is suitable for a frequency lower than 5 kilohertz, dynamic load flow, and when you model for some switching, triplex and 5-leg core. So triplex, what it is, it's when the transformer, it's built with 3 units physically. So in this case, it's kind of exactly the same representation, so no problem. 5-legged core, it's also a good representation for that. When you use this model for switching, you will have to add some stray capacitance on the primary, secondary, and between. The stray capacitance will reproduce basically the capacitance of the conductor with the ground and between conductors through the insulators. You know, anytime you have 2 conductors with an insulator in between, you are creating a capacitance. So when you have a winding sitting on a stator, you have a conductor with the ground, that's a capacitance. When you have 2 windings together, you have insulator in between, you have a capacitance. So by putting those capacitances, you may reproduce the high frequency behavior of the transformer. You have a paper written by April that explain how using the stray capacitance measured with a Dumble test, how you can find out the capacitance to put in the EMT software to get a good result. In fact, the reference, the outcome of that is pretty easy. When you measure the capacitance primary to ground, secondary to ground, and winding to winding, you multiply this value by 0.4, and that's the capacitance you should get. Okay, so the other model type here, the topological model. So like I said, here when you have a magnetic core, we will reproduce that using electrical circuit. Why is it important to model the magnetic core? Well, it's because let's say you have a 3-leg transformer like that, and you are in an open phase situation, you have nothing at the secondary, and for some reason you energize only one phase. Well, the flux generating in one phase will go through the other phases. And so you will see some voltage, basically 0. If you have 1 per unit on phase A, you will have 0.5 and 0.5 on the other phases because the flux goes there. If you are using a representation like this one, except if you have a delta connection, but if you have YY connection, you will not capture that. And so if you do some sort of open phase study, it's important to have that. So also when you have this transformer, you may simulate local saturation. If you have, for example, a 5-leg transformer, you will have here the return legs, and you have local saturation if some flux goes more through one part or the other. So this model, of course, it's more suitable for any time you study saturation. So for resonance, we worked a lot, again, with EPRI. We have a lot of projects with EPRI. It has been a big, very long-term partner since the really beginning of EMTP. Basically, EPRI was involved. There was actually an EPRI version of EMTP. And so here we could reproduce the events in Hydro-Quebec when there was a blackout due to a geomagnetic disturbance. So this model is also suitable for resonance, open phase, winding failure. You have the possibility to model in detail all coil and to do internal faults. So you will tell me, okay, but this model is probably require a lot of data. That's correct. It requires more data. We have an entry data set available where basically the core length is in per unit. So you may just reuse the same core length, and it's already not so bad because you have all the magnetic path. You may require also some zero sequence tests, kind of like with the BCTRAN. For the one of you that are used to work with BCTRAN, it's a little similar. So you may need zero sequence tests, which may be hard to find, but that's kind of it. Then if really you want to go in a lot of details, yes, you need to know the exact geometry of the core, and that's become more tough to find. Okay, and so the high frequency transformer, I discussed that a little bit already. I don't think there is really much to say here. Okay, so let's focus with the one that we are going to use most of the time for renewable integration studies. So this transformer, again, 3 non-ideal units. One ideal unit is like this. So typically, the minimum information you have in a transformer, it's the impedance, Z in percent. So basically, the Z in percent is the short circuit impedance of the transformer. So it's when you create a short circuit here, the impedance of the entire transformer. So it will be in series this RL and the one at the secondary. So those two in series will be your Z. Those two, basically, what they represent is the winding impedance, the winding inductance, the winding resistance. Okay, so the losses and the reactance. Then you have, of course, the ideal unit to rise or lower the voltage, and the magnetization branch reproduces the core. Okay, so you have in there losses through the resistance and reactances of the core. So those are the inputs you will give in EMTP. So the connection type, so that you have, you always have. The nominal power, this is easy to find. The nominal frequency, this is easy to find. The voltage on each winding, this is easy. Then you have X and R. So basically, when you are given Z or Z, it's the square root of X squared plus R squared. However, R is often very, very small compared to X. So most people make the assumption X equals Z, and so you will place your Z or Z value here. Let's say Z is 10%, you will put 0.1 per unit here, and that's it. If you want to be more precise, you can. But then remember, this Z value is the total between the primary and secondary. In a phasor domain software or short circuit package, you don't really care because you don't really have this point in the middle. And so that's why most of the time you only enter Z. But in EMT type tool, you have to say what percentage of this total impedance is at the primary and what percentage is at the secondary. And most of you will tell me that you never have this information, and you're right. Most of the time you don't have this information. However, this information isn't so often crucial. Basically, this information is crucial only when you are interested in the voltage in the middle point and how much it saturates. So when you want to simulate a saturation event like energization and so on, then you will have to dig a little bit and make sure to know what percentage of the impedance is at the primary and the secondary. So when you energize here, you know exactly what's the voltage here and how much saturates. But if you are doing a load flow or a short circuit and so on, it does not really matter how much percentage goes. So you can do 50-50 or put 90% of the primary, 10% of the secondary. So this can, it's something that is done very often. And so the last input here is the saturation branch. So the saturation branch is, like I said here. So you have the this resistance. This resistance you calculate it using the no load loss. So the no load loss, what are they? You connect on one side of the transformer, you apply a source, a voltage source, and the secondary is disconnected. So you have the current going like this. But because this resistance is much larger than this one, you can kind of approximate that there is no impedance here and that all the resistance is due to this, all the losses are due to this resistance. And so then it's basic, you can calculate directly what is the resistance here. And so for this nonlinear inductance, you have to provide a current flux curve. So this is a bit more tough to find out. I will explain you how to do after. Okay, one question here. So the values of impedance are not important for the switching studies. Yes, they are very important, of course, for several things. So the value of impedance when you switch, when you do a switching study, the overall voltages you get depend on inductance and capacitances. Okay, so when you do a switching study, you have to evaluate all inductances close by to your switch and capacitances very precisely. So those are very important. Now the setting, the parameter I was discussing before is this one, winding impedance on winding 1, which is the proportion of total impedance at the primary of the transformer. So this one, when you do a switching, it's not so important because when you do a switching, you have high frequencies, and for a high frequency, will not really get to the middle point here. Because for a high frequency, you have this inductance, which is kind of big. It will behave as an open circuit. So when you do switching lightning, here the voltage will not really change during the time frame of the study, which is less than a cycle. So it's not so important anymore. But if you do a energization, then it's important. So energization, it's also a switching, right? Okay, so we have another question here for the magnetization data. Can I answer VI curve from manufacturers? Yes, absolutely. So that was the next point here. One routine is to go from the VI curve. So the VI curve, it's an RMS curve. When the transformer is in open circuit, manufacturers will apply a voltage, 1 per unit, 1.05, 1.1, and measure the current in RMS. And it exists a routine to go from this RMS value to instantaneous current flux for this nonlinear inductance. So we have the same in EMTP, the exact same routine. You can use it. This routine in the current version works for YY transformer. And so for Y delta, you have some extra manipulation to do. We will do that during the lab in order to fit better the result when you have a delta. Because what happens when you have a delta is that you have some harmonic trapped in the delta, and it will not be so easy to estimate them. In a future version of EMTP, probably not the next one, but the one after, we will give the option to enter directly the VI curve for any connection. And so we'll apply automatically this transformation. Another question here. When doing detailed modeling of the transformer data, the information of the core design may not be generally available. In the absence of such data, how far can we go ahead with the modeling? Or do we make some basic assumption to proceed with the modeling? So, well, good question. Like I said, most of the time for renewable energy, we will use this representation here because we're interested in short circuit studies, stability studies, and so on. Now, if we do the studies that I explained here, which are saturation, ferroresonance, and so on, the other model here may not be valid anymore. Then you will need this one. In this one, you need the core, you need to know the core type. I think it's generally possible without so much effort to know the core type, if it's 3-leg, triplex, 5-leg, etc. This you can find out. then you can use per unit values. What is very important, there is a major difference when you compare 3-leg and 5-leg. The difference when you have a 5-leg is that it exists a return path for the flux without going through the winding. So that's the major difference. And so if you use the per unit data, you just simply specify what type of core you have, 5-leg, then there will be some data in per unit, and it's already very good. And it's probably better than most things that you can do with the other models. And so that's kind of what you should do if you're interested in saturation. If not, then you use the other model. Other question, if you uncheck the box next to % of R on winding 1, does the default or exclude? So if I uncheck this box, basically you will get the chance to give directly R1, L1 and R2, L2. I can show you in the tool here. If I drag and drop a transformer, okay, and I uncheck this box, okay, then now you have to enter R1 and R2, X1 and X2. Okay, and so if you check it, then you enter the total and the winding impedance %. Okay, I'm here. Mihailo, any question I may have missed? I think that I see there's a lot of questions. I think I answered all of them.
Well, there is a question about the tap changing.
Oh, okay. Can you read it out?
Well, it just says, is there an easy way to model tap changing on the transformer?
Yes, there is a very easy way. The easiest way is basically to put in series here another transformer where you put 0 impedance, and you put your tap here. So you put basically 1 and 0.9 and 0.95. So that's the easiest way. Then it's like always, it depends what you want to do. If the goal is actually to see the movement of the tap, okay, which is a very slow process, then you need to model the control. And because it's not completely the topic of the training, we have limited time, I will point out where the example is. And if you need more information, you may contact us and we can show you in private. So if you go here to the application cases of the software, and you scroll down, you will see here tap changer. Okay, and you have here this example. I will open it very quickly to show you. Okay, you have this example here where you have 3 winding transformer with tap, and the tap control is here, and 2 winding transformer with tap, so you can check out this example. Okay, I see another question from David. Is it possible using the most simplified model to observe behavior that may indicate that you need to move up to the next higher of level or of detail of the transformer model? In other words, how will we know? That's a very good question, David, and it's that's kind of the challenge we have as engineers. I would say it comes a lot with experience. For people that I guess do a lot of transformer modeling, and it comes naturally. The way I like to work is, often when you do power system studies like in EMTP, you will end up running many simulations. You will do parametric studies on the contingencies, sensitivity analysis, and so on. And so before doing that, I like to spend time to see what have data. And the way I like to work is to start with the most simple version as possible, obtain some results, and then add some more sophisticated model and enlarge the size of the network. For the transformer, what you can do if you're not sure is first run the simulation with the 3-phase nameplate input model that we are showing now, and then use a better one. Even if you have missing data, you put typical data and you simulate that. If you have results, it means that it has an impact. If you see a difference in result, it means it has an impact. You should refine. But it's a bit tough for us to put a flag saying whatever you are doing, you should use this model, because EMTP, it's not organized as a toolbox base. It's organized as you build a circuit and you run and simulate what you build. So we don't really know what the user is doing. You just basically build your circuit and run. So that's why it's tough for us to raise flag and tell you you're not using the good model, because we cannot really know, especially in the case of transformer. Okay, so here you have written on the slide what I explained and how to fill out the table. So for the magnetization resistance, which is here the data. Okay, that's how you calculate that. Often, you know, the data provided in the data sheet, they have a certain precision. It can be between 1 and 5 to 10%. So most of the time, there is no need to try to calculate very precisely what is the good value, because often the value you get are not so precise already. So for the magnetization resistance, like I said, most of the time during test, a voltage source is applied here and there is some losses, and we assume that the voltage applied here is the same as the voltage applied here, and all losses are due to this resistance. In reality, some losses are also due to the winding resistance. You can, if you want, calculate R this way very precisely. However, most of the time, what you do is you take the losses in per unit, you take the inverse of that, and it gives you the resistance in per unit. And so that's how you do. A typical value for the resistance here is 800 per unit, for example. When you do ferroresonance study, for ferroresonance study, losses are very important. So in this case, you may want to evaluate that with more detail. All right. One slide that I skipped here, it's about initialization. When you perform a switching study for a transformer, you know, in the transformer, the flux is not really zero at any time. There's always what is called a residual flux. The residual flux is very important because when you will energize the transformer, the flux, instead of starting at zero, it will start at this value of residual flux, and it may enter into saturation quicker. And so when you do a switching study, the goal is to find out the voltage sag. You have different ways to do that. Either you simulate very precisely the de-energization of the transformer, modeling in detail hysteresis and so on, and you find out what could be the residual flux. This is a very difficult study to do because you have many unknowns. So the other way, which most people use, is a conservative approach. You will set residual fluxes here as an input and energize the transformer and do a switching study to energize the transformer. And then you find the voltage sag and the inrush current and so on. So this is what is done mostly by most people. Okay, so far we have explained how to find the inductance, this resistance. This resistance here, I skipped actually, sorry about that. To find it, you have two options. You can either have the ratio X over R and then calculate R with that, or you may have the load losses. The load losses, it's also a standard test where the transformer has 1 per unit of current going through it, and you have the losses. But in this case, most losses are due to these resistances. Almost nothing is due to that. And so you can basically just calculate R based on that. I probably have a slide on this somewhere. No, it's probably, yeah, it's here during the lab. I will show you that right after. Okay, and so in this slide, we explain how we find this inductance based on, so that was the question we had earlier, based on RMS value. Okay, so based on RMS value, we use this tool to go from RMS value to instantaneous. This is for the small model. For the more advanced model, the topological based model, we perform optimization. So when you enter all your value, you press OK. For 30 minutes, the transformer will run many simulations will be run on the transformer in order to adapt all parameters. It's an optimization study. And so at the end of the day, you have a very good model. Okay, I see a question. Will the typical value of residual flux from de-energization be a percentage or some parameters of the transformer? No, not really. The residual flux depend on many things. Of course, it depends on the parameter of the transformers, but also on the load you disconnect, the material, the hysteresis curve, how the core is built. So it's when we start to put our finger into something, you know, big when we look into that. So that's why it's difficult to use this approach to de-energize to find out what's the residual flux. It's a difficult study to do. Okay, so this is what we're going to do in the lab. Model this transformer. I pass on that because time is running. but you have the slides if you want to see a concrete example with numbers. So here, basically, it's a park transformer, 75 megawatts. On the collector grid, we have 30.4 kilovolts. The transmission grid is 120. Okay, and we have here the load loss. With the load loss, we find the resistance. We have the total impedance. We find X. We have the open circuit loss. We find the shunt resistance. And then we have this curve here, VI, to find the saturation curve. One thing that I forgot to say is that very often the open circuit tests are done up to the elbow of the saturation curve only. You will not find a point very far away in the saturation curve, which is very unfortunate because this is the most important point. When you enter into saturation, very quickly you will go after the elbow and you will start saturating the last segment, which is called the air core inductance. And so this value is often not known, and you may have to run many simulations, do the study several times, and changing the inclination of this last segment of the saturation curve.